Hello everyone. Today I'll be presenting Hodor, which is short for High-Level Object Descriptors for Object Resegmentation. Hodor tackles the task of video object segmentation, in which we are given the object masks for the first frame in a video, and the task is to track and segment these objects in the remaining frames. Existing state-of-the-art approaches work by learning so-called space-time correspondences, or in other words, correspondences between pixels across a pair of video frames. Based on these correspondences, the object masks in a given image can then be propagated to other frames. However, training existing methods to learn these correspondences requires video data with temporally dense object masks, which are costly and time-consuming to annotate. The question we pose is, do we really need labeled video data for this task? What if we could instead use labeled images to train a method for video object segmentation? This would be very useful because current image instance segmentation datasets contain orders of magnitude more labeled scenes than video object segmentation datasets. To enable effective training on single images, our method adopts a different paradigm to existing methods. Instead of learning pixel-to-pixel correspondences over time, we encode each object in an image into a robust high-level object descriptor. The idea is that we can then decode the descriptor in another video frame to track or resegment the object in that frame. Hodor has an encoder-decoder style network architecture. The encoder takes as input an image feature map and a set of object masks, and outputs a descriptor for each of the objects as well as the background. The decoder can be seen as the dual of the encoder. It takes as input the object descriptors produced by the encoder and image features from a different video frame, and outputs the segmentation masks for those objects in this frame. Both encoder and decoder have a transformer-like architecture consisting of several attention layers. During inference, we run the encoder to learn object descriptors from the first frame ground truth masks and then decode them in the next video frame to obtain masks for the second frame. We then rerun the encoder using the predicted second frame masks to generate an updated set of descriptors, which are then further decoded into the third frame. Likewise, these steps are sequentially repeated to propagate the object masks across the entire video length. In terms of training, our novel problem formulation lets us train Hodor on a single static image. To do this, we encode the objects from the image into descriptors and then decode them back into the same image. The loss then enforces that the output masks should be identical to those given as input. Now you might think that the network could learn to trivially copy the input masks, but actually the way in which our object descriptors are learned involves an information bottleneck which prevents this from happening. This was the basic use case, but our method also offers additional flexibility for training. Let's say you have a video dataset where just one frame per video is annotated. The question then is, can we somehow utilize the unlabeled frames for training? With Hodor, the answer is yes. First, we follow the same workflow as you just saw to propagate the object masks from frame 1 into frame 2. But then, because we don't have the ground truth masks for the second frame, we use the principle of cyclic consistency and propagate the object masks from frame 2 back into frame 1. So the learning signal here is that the predicted masks for frame 1 should be identical to those given as input. It is worth noting that our network is end-to-end differentiable, so the final loss can be back-propagated through the cycle to the first input. Here we see experimental results for different types of training data. We evaluate on the DAVIS 2017 validation set and report the JNF metric in this table. We compare Hodor to STCN, which is a recent state-of-the-art video object segmentation method. When trained on single static images, we achieve 61.6 JNF, whereas current methods simply cannot be trained in this setting because they inherently need multi-frame video data for training. Then we train on static images by augmenting them into a fake video sequence by applying random cropping and affine transformations. This is a common training strategy for VOS methods, and with this setting we obtain 77.5 JNF, which is better than what STCN gets. Next, we show results for training Hodor on video sequences where just one frame per video is annotated. This improves the result to 80.6 JNF, and it shows that Hodor can effectively utilize unlabeled frames during training. This is again a setting where existing methods cannot be trained without making non-trivial changes. Finally, here is a qualitative result video showing Hodor segmenting Hodor in a couple of video scenes. We hope that you'll visit our poster booth and GitHub page. Thank you for listening.